In this video, I'm going to briefly talk about some of the practical aspects when you're using and implementing neural networks. I haven't covered everything in this little series of videos. Of course, there's way more to say, but I just wanted to mention some of the practicalities of neural networks. So the first thing is a little bit about the different names. So we've looked specifically at feed-forward neural networks, but they're sometimes called multi-layer neural networks. They're called multi-layer perceptrons. They're sometimes called artificial neural networks, or sometimes just deep neural networks. So if you see all of those things, I mean, this terminology isn't exact, but very often those names refer to feed-forward neural networks. I would say the two most common names that's used these days when we refer to these specific neural networks that I looked at in this playlist is feed-forward neural networks and multi-layer perceptron. Those two terms are what's used to refer to these type of neural networks. There are, of course, other types of neural networks. Convolutional neural networks and recurrent neural networks are kind of the other two classes of neural networks that's really worth knowing something about. Also wanted to say about how we actually build these neural networks in practice and how you implement them. Of course, you use probably a package like PyTorch or TensorFlow or JAX. But then coupled with this package, you will probably have to fiddle with things to get things working. So it's very often useful to scale your inputs into the model. So in general, in machine learning, we very often scale things to have zero mean and unit variance. And in neural networks, it also turns out that sometimes it's useful to do that. Okay. In practice, they even have normalization layers that they incorporate in between different layers if you have a very, very deep neural network. In this little playlist, I consistently refer to kind of the normal gradient descent case. And actually, most of my examples, I just had a single training example. You can easily extend that to having a batch or more training data. And normally, it turns out you're just summing things. But in practice, we don't use vanilla gradient descent. You probably use some advanced form of gradient descent. Adam is very popular at the moment and has been for a number of years. So you can, in PyTorch, if you have to select something, or TensorFlow, Adam is a very popular optimization method. It is a gradient descent based method, but it does some special things inside to make sure that the models train easier. There's also many different initialization strategies. So we've spoken about this. Normally, when you train a model, you start with random weights, and then you do forward and backward and update the weights, forward, backward, update, and so on. It turns out that where you start out your weights is actually can be quite important. And if you go to machine learning conferences these days, you would probably still find a paper proposing some new initialization strategy. If you don't believe me, I think this is a paper where I'm a co-author on proposing an initialization strategy, one more. But you can probably just use the defaults in PyTorch, TensorFlow, or JAX. Overfitting in machine learning is always a tricky thing to deal with. And in neural networks, you can combat that using standard regularization techniques like L1 or L2 regularization. But I would say, and this isn't used that common, a very common regularization approach is something called dropout, where you basically randomly zero out some of your intermediate units. And that turns out to work really well. Stochastic gradient descent, which you use to optimize this, or even if you use the Adam variant, is also actually a way of doing regularization. So very often what we do is, while we're training, after every pass through your data, you evaluate the model on the validation set, and then you see, is this model at this training point, is it overfitting to my training data? Is it still doing well on my validation set? Is the performance on my validation set still improving as I'm training for longer and longer? And then that way, actually, gradient descent itself becomes a regularization approach, right? With neural networks, you need to make a ton of decisions. You need to choose the learning rate of the model. If you use dropout, there's some hyperparameters there that you need to choose. Even with the simple feed-forward neural networks that we've looked at in this playlist, we've seen that you will have to choose the number of hidden layers and the number of units per layer. So there are many decisions that you need to make. And unfortunately, sometimes these decisions turn out to have a big impact on downstream performance. And what I do now most of the time is, if I'm working on a new task, I try to find a paper or an implementation or a blog post that already tells me roughly what the architecture should look like. And then I start with that architecture and then I basically fiddle with it, just to have a good idea of where to start at. There are also other decisions that you will need to make regarding the architecture. So there are things called skip connections. So this I should maybe take a step back. Very often, as your models get deeper and deeper, you start to get problems with gradient descent. So they talk about exploding or vanishing gradients, and you need to deal with that. So this is basically when the gradients, these little delta U terms of ours, if it turns out that they sometimes grow to infinity, they get very large, or more common, they actually die out and they go to zero, and you might want to deal with that. And there's architectural ways of dealing with that. Skip connections is one of them, and you can read up a little bit more on that if you want to. I've already mentioned some layer normalization approaches, which are also often used. So this is this is a very high level view. I didn't go into any of the details here, but it's just to give you a rough feel for the type of things that you will need to know and look at when you're implementing neural networks in practice. It's not a science, it's an art.